For my Systems Lab final project, I worked with Jenny Fang to place a UAV into hover using dynamic inversion. Dynamic inversion is a technique used to control a system in a linear fashion by canceling out known nonlinearities. For example, take the following system x dot, where f of x is a nonlinear function. Suppose you want the system to follow a desired linear model L. The following command u equals L minus f of x over g of x uses dynamic inversion in order to transform the model such that x dot now equals our desired L. The following equations describe the UAV's vertical channel dynamics for z, vertical height, and omega, vertical velocity. The state equation for omega dot contains f of x, which describes the nonlinear forces such as gravity and the Coriolis effect. F of t is the force of the thrust provided by the motor speed u. The Coriolis effect describes the force acting on a body moving along an inertial frame. Our original model accounted for this effect. However, the Coriolis force was deemed to have a negligible effect on the output command. Therefore, we simplified the state equation for omega by assuming that the Coriolis force was 0. Our goal was to use dynamic inversion to create a linear command that governs the nonlinear movement of the UAV in its vertical channel. We could then use output feedback to make the UAV follow a desired model to track any desired hover height. A second-order transfer function was used to model the UAV's response to a vertical height command. These state equations show the desired model for z dot and omega dot. The transfer function that describes the space model is also shown, where zeta is the damping factor and omega n is the natural frequency. We then used the concept of dynamic inversion to create a new input u that would force the real dynamics of our UAV to resemble our desired model. This input u cancels out the nonlinearities of the system, so we can therefore achieve our desired UAV dynamics for vertical height and velocity while tracking a height command. We then decided our desired system response behavior by selecting the damping ratio and natural frequency of our system. We set the damping ratio to be 0.707 and the natural frequency to be 1 radian per second. Looking at the step response of our system, you can see that this parameter selection allowed for a rise time of 4.44 seconds and an overshoot of 4%. We had previously developed a Simulink model with feedback systems respectively commanding throttle, elevator, aileron, and rudder to stabilize the UAV in a hover by using the input command u equals -k times the respective state variables for each of the decoupled chair systems. We had also used Kalman filtering to provide more accurate state feedback. We then implemented our new feedback control system for throttle by replacing the old input command for u with our new one. Shown is our UAV tracking a 1 meter height command using our new throttle feedback control system. As you can see, there is a large height overshoot during takeoff and drift in the X and Y axis during steady state hover. To fix these issues in drift and oscillation, we retuned the gains for the elevator and aileron linear quadratic regulators by adjusting the parameters for each of their respective cost functions. In addition, integral feedback control was added to the elevator and aileron control systems to help eliminate drift of the UAV in the X and Y axes. Overall, these changes helped achieve a very stable hover around 10 seconds into the flight, as the UAV tracked a 2 meter height command. However, this takeoff does not appear to be the most energy optimal, as there is a lot more height overshoot when compared to the previously used bang-bang takeoff method. This could perhaps be fixed by adjusting the damping ratio and natural frequency values to allow for a longer rise time. Another issue with the initial takeoff could be due to faulty sensor readings. While we did reconstruct the states using Kalman filter, this method was not robust enough against the very wrong altitude sensor readings during the first few seconds of takeoff. Due to the sensor measurements reporting incorrectly small altitude measurements during the first 2 seconds of the flight, the throttle feedback control actually commands the UAV to go higher despite it already being much past the commanded 2 meters. In our original system, the feedback controller for throttle required linearization of the UAV's state equations for vertical height and vertical velocity around an equilibrium point. We successfully replaced this control law using dynamic inversion to eliminate the UAV's nonlinear dynamics and replace them with a model that follows a second-order transfer function. Since this control law is not dependent upon linearization at a certain point, it is perhaps more robust to different flight commands. Overall, we achieved a stable hover using dynamic inversion to track a height command. Thank you to Jenny Fang, my lab partner, for her assistance in this project. Thank you, Dr. Bond, for his help during both this project and the entire semester. Thank you for listening.